Sorbonne Paris-Nord. So he's going to speak about trajectories and asymptotic of resonances. So please, you can start.
Okay, so thank you for the invitation. I want to thank Wafa, Ayman, and Michele to give me this opportunity to give a talk. So this is in some sense based in some work with Jean-François Bonny from Bordeaux 1, Setsuro Fourgier for Ritzmaken, and Thierry Ramon for Paris-Saclay. And also, I hope I give the statement with my work with Johannes Sjöstrand, the later one. So please, I state, so I use another, not Acrobat, so I must change a little bit to write some word and so on. So the outline of the presentation is I introduce what is it, resonances and the relation between the truncated resolvent, and also I introduce a trapped set, and we defined also the resonances by other methods to prove our results. So after maybe, so it's very slowly the first step to give what's the goal, and I explain the previous result and some methods, what it didn't work for our result. The second, so the second thing is our main theorem with Bonny, Ramon, and Fourgier, what we called multi-barrier potential. And for this potential, I give two examples, but there is a lot of variety of geometry here, and there is a lot of asymptotic of resonances and a lot of phenomena. I cannot explain all these phenomena, but maybe two or three what are different from the later work. And finally, maybe I explain the geometric setting for some level and the main result with Johannes Sjöstrand. So please, I start with, of course, it's concerned the semiclassical Schrodinger operator. So minus H2 Laplacian plus some potential. And here H is a semiclassical parameter. And we assume that our potential goes to 0 at infinity. So maybe, yes, I want to give a picture here. So here for the spectrum, so here we work in C. Excuse me. So the spectrum of P is 0 infinity. So this is the essential spectrum, and possibly maybe there is some eigenvalue if, of course, we assume this hypothesis at infinity. So V is bounded from below. Here, if we consider our potential, something like maybe like this. Okay, so this is the spectrum of our semiclassical Schrodinger operator. And of course, we recall that the essential spectrum is the complement of the discrete spectrum. So the eigenvalue with the finite multiplicity. This is a general fact. So the idea now is to consider, so here maybe I draw in red the essential spectrum. And we know that since our operator is self-adjoint. So for imaginary part of Z, different of 0, P minus Z minus 1 is well defined as a bounded operator from L2 Rn to H2. But we know, because you have a essential spectrum here, that the representation is different if you are in imaginary part of Z positive or imaginary of Z is negative. For example, we can, in R3, we know that the green function is exponentially EZ x minus y over 4 pi E x minus y. And for imaginary part negative, you have exponentially minus EZ modulus of x minus y over 4 pi modulus x minus y. So you know that this is well defined, and we want to cross the essential spectrum. Of course, if you take the green function alone, this is it's not evident at all. But if you truncate, if you consider this resolvent, so maybe I can write minus P. This resolvent minus 1. And if you truncate this resolvent, to both sides, we can cross the essential spectrum, and we have a theorem and a definition. If you consider this resolvent defined from real Z positive and imaginary Z positive with the value in L2 compact to H2 lock, that admit the holomorphic extension to the lower half line. So we can extend this green function, and we obtain a holomorphic function, excuse me, a meromorphic function with pole in the lower half plane. And this poles are by definition, so these poles are by definition is the resonances of P. So this is the abstract way to define the resonances of a self-adjoint operator, okay, who admits essential spectrum. So on the other side, if you consider the semiclassical symbol of P of our Schrodinger operator is given by x square plus Vx, in what sense that our P is the Veil quantification of the symbol P, like this. And if you consider the Hamiltonian vector field HP defined in the contingent of Rn by HP is dxip minus dxp. And if we consider the Hamilton curve here, we can define what we call the trapped set at energy E0. So for the moment, please give me 2 minutes to explain two facts very important. The very important thing, if you take the derivative of P at some Hamiltonian curve, so this is essentially P, the Poisson bracket of PP, and this is a 0. So in the sense that P on the Hamiltonian curve is a constant. So the Hamiltonian curve lives at energy E0 of x0 c0. It's in the energy E0. This is a very important fact. So the energy create a foliation of the cotangent of Rn. So if you have, for example, P minus E0 here, so the different curves lives in the same level. This is a very important thing. And the idea is to understand what is the relationship between the resonances or the distribution of the resonances of the asymptotic of the resonances with these trajectory. Okay, this is the first thing, very important. And we define the very important object, classical one, is the bounded trajectory, what we call the trapping trajectory. The set of trajectory is the trajectory like this, who didn't go to infinity. This is a very important thing. So to understand this relation, of course, there is the abstract way, excuse me, so to define the resonances as a pole of the truncated resolvent. But in some sense, if you want to have an asymptotic and to precise the location of resonances, we want to have the relation between this quantic quantity and the classical one. And for this, the first thing, very important, we can show after that such energy for the distribution of the resonances is not important. And the very important object is this. And for this fact, you have other methods, and maybe I explain only the method we use here, what we call the complex distortion. So what is it, the complex distortion? So you must assume that our potential have an analytic extension in some domain near the real. So here you have Rn. And we assume that our potential have some analytic extension in this sector near R. So we don't need that to be analytic near all Rn. So what we call essentially no globally analytic potential. And if you have such an assumption, we can define what we call distortion of Rn. So we distort the manifold Rn by using this unitary operator U for mu real. And after, we can complexify mu, but mu small. So what is it exactly? In Rn, we can identify some what we call a totally real manifold. Is something like this, and real here, what we call gamma theta. Okay, and our operator now P, of course, it defined on Rn, and it's real on Rn, but we can extend it to the manifold gamma theta since we have this assumption. I'm sorry, because I don't look the color. Excuse me. So since the potential V can be extended in analytic way, we can restrict our operator P to gamma theta, to this manifold, the red one. And now, because gamma theta is not Rn, so our P is not longer self-adjoint. So it's a non-self-adjoint operator. and possibly he can have some eigenvalue complex 1, okay? This is the idea. The very important fact that when this distortion mu, when mu is real, our distortion is unitary, okay? So you have two facts that for theta real, our deformation is unitary, and for theta complex and small, you have some p operator non-self-adjoint, okay? So we defined the resonance of p, so it's a spectrum of p on gamma theta. Maybe I explained 2 points here, very, very important in this setting. So here 0, if you remember, you have the spectral of the essential one of P, sigma essential of P, excuse me, up. And now after a distortion, we have P theta, and we want to understand what is it, the spectrum of P theta. So with another color, the spectrum of P theta the essential spectrum becomes here with 2 theta. And because now it's non-self-adjoint, maybe we have some eigenvalue complex 1, okay? This is a very important thing. So of course, there is a lot of question here to understand what is it, if someone delayed with some theta, another with the theta prime bigger than theta. So for example, if you take theta 1 than theta, and the essential spectrum of P theta 1 now is here, and you have 2 theta 1, and the very crucial point is you discover the same eigenvalue in the sector given by P theta, but also maybe other. So this eigenvalue, it didn't depend on the techniques, it didn't depend on theta, it didn't depend on the distortion F also we can show, and this is by definition, so is the resonances of P. Why this definition is very important? Because in some sense, we define the resonances of P as eigenvalue of non-self-adjoint operator P theta. And for P theta, we can control his semiclassical symbol, who is, of course, no longer real. It becomes complex. So this is a very important thing. And of course, to prove that it's the same, the definition are equivalent, you have the first step. If you take a cutoff, but if you take a cutoff exactly here, so maybe another. So if you take chi here, in the region who didn't do the distortion, you have this identity, okay? So the resultant on P is exactly the resultant on P theta, and the pole of this resultant is exactly the same of the pole of this resultant. Of course, this technique is done on more general, is to distort all the cotangent bundle of Rn This is by what we call escape function. So it's a generalization of this method, and this method is done in 86 by Elfer and Shostrand. And the very important thing is this definition are equivalent and is proved by Elfer and Martinez in 87. This is a very important thing. So now, what is it, the question? So what is it the asymptotic of the resonances in the case of particular geometry of the set of trapping trajectory? This is a very important problem. So maybe I explain some well-known result, and to focus after the very important thing that having some geometry, it's not easier to understand the distribution of the resonances, and it's not usually a lattice or in some line and so on. This is my goal here. So the first result is implicit in Elfer-Shostrand 86, and after is proved by Martinez in the setting of non-globally analytic potential. And here is very, very, in some sense, very simple. We use only the ellipticity of the dilated operator. In what sense? Taking, for example, a potential like this. Okay, and we consider, for example, some energy here, E0. So essentially in this presentation, E0 is positive because we took the limit, or the essential limit of our potential is 0. If not, we can translate. And if we take this shape in the cotangent space, and P minus 1 E0. So here, it's not good, but anyway. So here in X and Vx, this is important. Here is in X and Xi. Maybe I choose a color. So, and the trajectory here, and excuse me. So, and the limit, of course, at infinity of V is 0. So the asymptotic here is square root of A0. And here, all the trajectory goes to infinity. So we can find an escape function G or a distortion Rn such that, so here, so maybe I change. So here, the set of trapped trajectory is empty. Okay, and we can find some distortion that our operator P theta here for some theta and elliptic. So if P theta is elliptic, so there is no eigenvalue of P theta, so no resonances for P. And of course, they show that the very important thing that near E0, so here is in complex plane. So essentially, from now, every time I fix a potential, I fix the behavior of the trajectory, and after the spectrum, so they show that there is some neighborhood in the analytic case. So it's independent on H, that there is no resonances here. This is very important. No resonances. There is no resonances here. And in the case of non-globally analytic potential, Martinez showed the same result, but here the constant C, it depends on H, it's exactly H log 1 over H. Okay, but it's only a technical fact to control the different error in the asymptotics behavior. So the second example, very important, is the example, the well in the island, and what we call the shape for resonances, and it's related to the tunnel effect. This is a very important. So what is it essentially? So I do the same. And I consider exactly E0 and here if we the cotangent of Rn, so it's a point who correspond to this point. So this is the minimum, local minimum of the potential, okay, the point, and after so the same fact, all the trajectory who are unbounded, who goes to infinity, we can find a distortion such that our p theta is elliptic, and in fact is depend only on this point. And this is the idea if we want to understand essentially if this you have a particle here, we cannot reach, okay, it's the minimum on all direction. So you cannot see in some sense the C. In some sense he's confined, and of course the better thing is to have the harmonic the harmonic approximation here, and of course when the energy, so like this. So the problem now, it reduces a problem of eigenvalue of, for example, Dirichlet boundary. And Elfer-Sjöstrand show that the resonances in this case near E0 in some box, some neighborhood, what we call the shape. And the width here, this is a very important thing, that the imaginary part is exponentially small. So in some sense, is a perturbation of eigenvalue, okay, of the harmonic oscillator. The harmonic oscillator, their eigenvalue is look. So this is roughly speaking. So this color is not good at all. Okay. This is the eigenvalue associated to the Dirichlet. And this is the tunnel effect also. Okay, because the resonance state here is approximate, but we call pseudo resonances. The pseudo resonances here is this eigenvalue, and the pseudo resonance state is of course in this setting exponentially minus x squared over 2h, for example, the first one, and after the derivative, so the Hermite function and so on. And here the very important thing, this function is not zero in the classical forbidden region. This is a very important fact. And the exponentially small is given if you have here the trace of this function is not, of course, zero, but it's exponentially small. This is a very important thing. And of course, in this, in the first situation, we distort to have elliptic operator. In this situation, we have a model to compare, okay? And it's in some sense solvable model, okay? So in the case of hyperbolic trajectory, if you have the same potential and not near a minimum, so you have something like this, and we go far from the minimum here for this potential, and this is a minimum for one direction, and in the cotangent space, you have periodic trajectory, and this is very important. The same thing we do, we kill this by distortion, the unbounded, and now you have a hyperbolic closed trajectory, and this becomes an eigenvalue problem. And here, Gerard and Christian Gerard and Schostrand show that the spectrum near E0 is a lattice. This is very important. And we control the width, it's h, also here h for the real part, and so on. And the critical point in general, you have only a critical point. So in some sense, it's some minimum of m plus and m minus, the signature, and of course, non-degenerate. So m plus positive eigenvalue and minus negative eigenvalue of the Hessian of the potential. And they prove also some lattice structure, okay? And here we need only what we correspond to a maximum of the potential. So the negative 1 is 0 and the positive is n. So like this. This is our potential V. And we want some energy E0 positive. So in the cotangent space, this is very important. You have, and this is a new behavior. You have one Hamiltonian curve is reduced to a point, but also you have unbounded potential, but they go to this critical point. And here is very difficult to separate the unbounded curve and the bounded one. Of course, here, if you remember, every time we go to some distortion and we separate, there is a big separation between the trapped trajectory and the unbounded trajectory, in all this situation. This is a very important thing. So in some sense, the model is very hard to understand, and maybe also the behavior near the top of the potential, it's very important. So the behavior of this curve to go to this point is very, very important. Of course, when you have a maximum global one, we can do some canonical transformation. This is done in Schostrand 87. And also we compare with some normal form, and this is done by Kaidi-Kederue in analytic case, but in what we call in C infinity category is analytic outside a compact set, not globally analytic in some sense. This is we do, but we precise exactly what is it resonant state near this point. This is important, and essentially is very important. It becomes from creation and annihilation operator. So to write essentially the potential here after canonical transformation as harmonic oscillator, and if you write this like a c square plus x square as a symbol, we can write it also as a creation and annihilation operator, and this is the classical for the point of view. So now the very important thing, and this is only done in one dimension in 98, because we have some very powerful method, what we call exact WKB method, and this is in the case of hyperbolic fixed point and homoclinic orbit. So maybe I give the potential here. So it's like this. So here I insist is important that to be in dimension 1, okay? And we take the energy level. So it's not degenerate, this is not good, but okay. So here you have this fixed point, or the critical point of V. So in the cotangent bundle is a point trajectory, and also we have a homoclinic one. Of course, we can have also here some unbounded. So we do the distortion. Of course, here I forget. So after distortion, we can kill this. After distortion, we can maybe kill one of this integral. And after, we need to understand what is it, the solution of PU equal but U in some sense is not 0 here, is H infinity. Okay, and of course norm of U L2 is 1. And of course here we are in dimension 1, we can use this is very important for us after, we can use our solution U of X, and we propagate the solution along the trajectory in the cotangent space. And after we want to cross this critical point, and after to have some information after the crossing, and we finish turn out the trajectory, and we identify our solution after one turn. And this is give us, in some sense, a quantification rule. And in this case, Ramon and Fougier show that near this energy E0 positive, we have horizontal line before E0 and after some logarithmic line. I can show one picture after in our setting, because we improve this result in n dimension. in multi-dimension Schrodinger operator, not only. So we cannot use the exact WKB solution, but we use what we call Lagrangian distribution here. So this is essentially what we know, the well-known behavior and the relation between the eigenvalue and between the resonances, the distribution of resonances, and the set of trapping trajectory. So the second thing, I want to explain our situation and what we call the multi-barrier potential. So let me draw our potential. So the multi-barrier potential, we are in dimension n, and essentially bigger or equal to, okay? And we consider a potential like this in Rn, and we are interested to some level A0, and here the value of these maximum is exactly A0, but here is bigger than A0, huh? So A0 is red. And we want to understand what is it, the behavior of such situation, and the very important thing. So this is, for example, is S1. So maybe I wrote with different letter with the representation 3. So V of Sj is equal A0. So here the maximum is bigger, okay? And here, if you want to understand the trajectory, there is a lot of trapped trajectory between S1, S2, S3, and maybe they comes here, some trajectory, and go here, and so on. So what is it exactly in the cotangent bundle such thing? So maybe I wrote what happened exactly in this so in the with xxi, so you have some where Vx equal to 0, and you have some trajectory from side to side. And so on. If, for example, we reach some potential that his maximal is bigger than E0, you have trajectory like this, and so on. So this is the idea, and the very important thing in our situation is to understand in n-dimensional situation what happen when we cross such a point, the critical point. This is the very important thing. So you have a lot of what we call, so if we consider this situation, we have the idea that to have some vertices, this is who correspond to 1 point Hamiltonian trajectory, who correspond to some local maximum of the potential, of course, at energy E0, and some edge, okay, from one vertices to the other. And of course, we can have something who goes to infinity. But by dilation, we can delete one of them, and the other we can prove it's not, it's only to define the resonant state. So this is this is our situation. To understand what is the distribution of the resonances in such situation. Of course, there is a lot of situation if you have not only one trajectory, you have a sub-manifold from one point to the other. But this is also works in the same thing for the closed resonances near the real axis. Okay, this is a very important thing. So let me very quickly give the situation and the hypothesis. So here we decide that we have some finite set of vertices, and we have some edge between vertices, and we assume that between two vertices there is that when we go from vertices to the other, it's not empty. This is very important, and we call, but here I called here in this picture that we call homoclinic vertices if the started point and the end point is the same, and heteroclinic trajectory if the started point and the ended point is different. Okay. And we assume that our set of trapped trajectory is exactly these vertices and the edge with these vertices. So only for a computation, this is very important. We do some stationary phase and we want to have the leading term. If not, we must do some degenerate stationary phase. It becomes complicated, but it's not generic. And here we decide that if you go from one vertices to the other with lambda plus and lambda minus is transversal. So it's intersect cleanly in some sense is transversal. So the tangent of lambda plus intersect the tangent of lambda minus, and it's equal exactly the tangent at the edge E. And the final point is when we arrive, this is, we can understand the dynamics when you arrive to some vertices, and this problem is pointed out by Elfer-Sjöstrand for eigenvalue in Harper situation, what we call the expandable solution for the Hamiltonian flow. And here we need that when we arrive to some vertices, that the direction when we arrive and the direction when we pass is not orthogonal. This is very important to that the leading term not degenerate. And of course, this is generic. By a perturbation, we can do it. So as we explained, the very important setting here is, and adequate vocabulary is the graph vocabulary, and this is very important here. And we can explain the idea of cycle. What is it a cycle? What is it a path? So here, if I return here a cycle, for example, if you go here and here, this is one cycle. You can go there, and for example, here and here and here and here, another cycle. This is a minimal cycle, of course, if you have a homoclinic one. And we defined also what is it a primitive cycle. So for example, this is a cycle, primitive one, but if you take something like this, and that is not primitive because it included a primitive one. This is very important after to understand our asymptotics. So we defined what we call the damping coefficient. The damping coefficient is, in some sense, it's a tax to pay when we cross some vertices. And this is important because it takes account of the behavior of your Hessian near vertices, of the Hessian of the potential near the vertices. And here the lambda J is the eigenvalue of the Hessian of the potential. And in this setting, we defined what is it, the damping. So D0 is the minimum of this cycle. So I forget there is one important thing that the graph here is finite. Why? Because we assume that the lambda j intersect transversally. So there is at least between 2 points, at least n trajectory, no more. And if we define D0 as a damping, and we choose the word damping, thinking about the control theory, and this is very important for later work. And D0 here is very important. It's the principal part of our imaginary part of distribution. Okay, and here we call minimal cycle the cycle that give us D0. Okay, of course here the cycle are finite because you have a finite graph. This is very important. And as we explained very quickly in the Ramon-Fugier work, the idea is to take a solution to go around. So maybe here is very important. So if you take a solution here, you
Sorry,
cross.
Maher, I think your time is up. So maybe you can just try to conclude.
Okay.
Yeah, state
yes,
the result.
Excuse me. Okay, grazie, Michele. So the very important thing, you have a quantification rule. So you defined what is it, pseudo resonances, so the leading term. And after we do some computation on the determinant to give the importance of this damping D0, and you have this result that in this situation, E, our resonances, so it's E0 plus some perturbation in H, and this is very important. The imaginary part of the resonances is given essentially by D0. This is in macroscopic scale, and in microscopic is D0H plus some Z, who Z is zero of coding function, H log H. This is a very important thing. And this is, they give us just one important thing. So we reprove the theorem of Fugier and Ramon, and here maybe some simulation. If you take 3 bump, so the behavior of resonances is like this, is periodic. This is one fact. The second fact, if the geometry between the 3 bump is dependent, so you have, we do some simulation and you have accumulation curve. E0 is here. And here is D0. It's not 0. It's the damping. And if this is very important, if you are if the behavior between the 3 bump are independent, Q independent, so you have a cluster. There is no structure at all. This is a very important thing. Thank you.
Thank you very much. So are there questions? So we have just a little time for questions because but okay. There is still room for 1 or 2 maybe. Let's see. Let's see if there are other questions. Okay, maybe just a curiosity. Actually, I'm not an expert about this field. So, but so you discussed the resonances in the complex plane, right? But
yes.
Is there any way to apply this analysis to resonances on the real line, say a 0 energy resonance or something like that? So is there an, because of course it's key that the resonance is outside of the real axis, but there is an adaptation to that one can do?
So there is an answer. No, here, in fact, is the other side. The idea is to go more and more lower in the lower half plane. This is the idea, and to understand what dynamics. Until now, it's the real dynamics give us resonances more and more lower in the half plane. Okay.
Okay. So okay, but
so the strategy every time for the situation is to prove we have some band without resonances, the damping D0. And after we want to understand the dynamics, and we go more and more. And maybe one idea, the complex dynamics give us the resonances with the imaginary part is very, very larger in some sense, a modulus, of course.
Okay.
So not it's a I understand the situation, and it's